All right. Hi, everybody. I hope you guys are all doing well. So for this video, we're kind of just going to do an example of what we did at the beginning of 4.3. This was actually supposed to be part of that last video, but it didn't make it on because I don't know why it just stopped recording and it didn't save onto my cloud. So I couldn't find it, so now I have to re-record it. We're almost done with section 4.3. I want to go over this last example for the first derivative test, and then we'll move on to concavity and the second derivative test in our next video after this. So just to recap a little bit, the first derivative test allows us to find the minimums and maximums of our function and find our local extrema and identify our intervals of increasing and decreasing. So that's exactly what we're going to do in this video. So the first thing we always need to do is we need to first find our critical numbers and test them. So our critical numbers, recall that they can come from many different, setting our derivative and setting it equal to 0. That's usually how we find our critical numbers. But our critical numbers can also come from things that are undefined in our function. So the first thing that I would do before even taking the derivative of this is just to identify and make sure that we are identifying all our critical numbers from the beginning. Because if there's something that's wrong with the domain, then we have to also test our intervals there. So what we're going to want to do here is hopefully after seeing this function, your instinct told you that you wanted to do x minus 2 times x plus 2. And then divide it all over x minus 1 times x plus 1. So this tells me right now that in my domain, I have to exclude -1 and +1. That's because I don't want my denominator to be equal to 0 at any point here. So those are actually going to be our critical numbers, and we still have to test those as well. But that's just something that we need to keep in mind because at the beginning of 4.3, I just decided to do a very simple example just to get the point across, and I did a polynomial, which with a polynomial, we don't have to really worry about anything because it's all real numbers. So now that we identified what is in our domain and what is not in our domain, now we can go ahead and take the derivative. So remember that the first step to find your local extrema is to find the derivative. So we're going to find the derivative. So we need to find f prime of x. So right here, I encourage you to pause the video and try to get the derivative yourself and see if it matches mine. But I'm going to keep going, but go ahead and pause the video right now, and hopefully you end up at the same place that I did. Okay, so to take the derivative, my f prime of x is going to be x squared minus 1 to the bottom times the derivative of the top, which is 2x. By the way, I'm taking the derivative from here and not from here because this is going to be a little bit more complicated to take the derivative of. So if you're wondering how I'm going about this, minus the top times the derivative of the bottom, which is 2x, all over that bottom squared. So then we get x squared minus 1 all squared. Perfect. And now I notice that I can factor out a 2x here and a 2x here from the numerator, so I'll go ahead and do that as well. And then I get 2x times x squared minus 1 minus x squared plus 4. So here I just distributed that negative so that I don't have to do it later on, kind of skipped a step there. But here, after I factored out that 2, I distributed the negative right there so that we got it, and that's how I got that plus 4. And now we can just simplify. Then we get 2x, and then I notice that here, I have an x squared and it cancels out with this negative x squared. And then I have -1 plus 4. And so that's going to give me a positive 3. So times 3 over x squared minus 1 all squared. So this means that my derivative is equal to 6x over x squared minus 1 all squared. Okay, perfect. So now we have our derivative. And now our second step is to take our derivative and set it equal to 0. So our second step is always to find our critical numbers. And the way we do that is by taking the derivative and setting it equal to 0. So we're going to do f prime of x and set it equal to 0. So this means that we have 6x all over, wait, what happened? 6x all over x squared minus 1 all squared, and we're setting that equal to 0. Perfect. And so here, the only thing that's going to cause this to be 0 is if the numerator is 0. And so that means that 6x has to equal 0. And so that means that the only critical number that we have here is that x equals 0 is our critical number. Perfect. And so we found our critical number, and now remember that our third step is to now test our points. And so we're going to test our points, and we found one critical number using that derivative test. And so our one critical number was 0. And so all we have to do is test 0. No. We also have to test -1 and 1, because remember that our function was not defined there. We had actually we had vertical asymptotes there. And if you remember back to the beginning of 4.3, let's see if I have it here. Yes. At the beginning of 4.3, we had a function where we had an asymptote right here, and then it went from increasing to decreasing. And so we have to make sure that where we have asymptotes or where things are not defined, that we want to identify if our behavior of our graph is changing. And so we still need to test those points. Now, obviously, you wouldn't get a minimum or a maximum at x equals 2 because it's not defined there. We have no points there. But it can ask us, hey, is the interval increasing and decreasing? And then if you don't test that asymptote, then you might not get that it went from increasing to decreasing at that undefined point. So we always need to check. Okay, so now back to our example. So now that we know that we need to test those, it may or may not be the case that they give us anything, but we still need to make good habits of testing these things. Let me move this over a little bit so we can get a little bit more space. And then remember that we always test at our derivative. So we want to test here, and here, here, and here. So we are testing our derivative to see if our derivative is negative or positive. Okay, perfect. So now that we know that we have to test our derivative, what we want to do is, I want to test a point before -1, between -1 and 0, 0 and positive 1. Sorry about that. This should be a positive 1. Zero and positive 1, and then right after 1. So I like to do the easiest numbers possible. So over here, I'll do something like -2, here -1/2, here +1/2, and then here +2. Now remember that when you're testing the derivative, we don't actually care about the value that we get. We don't care about that numerical value. What we care about is the sign of that numerical value. So we care whether it's negative or positive. And so this is why you don't always need to actually calculate it. There's some times where you actually do have to calculate it because it's not so easy to tell. But for this one, I want to show you a little trick. My denominator is always going to be positive because I have x squared minus 1 quantity squared. If you square anything that, even if it's negative, it's always going to be positive. So the only thing that's going to cause anything to be negative is the numerator here. So the only thing that's going to cause anything to be negative is 6 times that number. So we can kind of just look at what we're plugging in and identify, is that going to be negative or is that going to be positive? And that's how we can identify the sign of that function. So for example, if I plug in -2 into this, remember, we only care about the numerator in this case, right? So if I plug in -2, 6 times -2, that's -12, that's a negative number. And so that means that we are decreasing here. And then similarly, if we do that with -1/2, that's also going to cause that to be negative. So we have decreasing there. And now if we plug in +1/2, that's going to be positive. So that means we are increasing in our function. And same thing here. So in this case, where our function was undefined, our function didn't behave differently in terms of increasing or decreasing, but we still needed to, check, because it could be the case that that does happen. So for example, if they asked you, like in this question, they didn't ask you to find the intervals of increasing or decreasing, but I could definitely ask you this on a test, then you would say that you are decreasing from -infinity to -1, union -1 to 0. And the reason you would have to union that is because we are not defined at -1, so we have to exclude -1 from our domain. And then increasing from 0 to 1, union 1 to infinity, again, because 1 is not defined in our function. So we have to be really careful with what we're allowing to be in our intervals of increasing and decreasing, and make sure that it's a good habit to, from the beginning of your function, identify if there's anything that's going to cause you issues or domain issues, and take those out of the domain. So when you end up testing things, you make sure to take those things out as well. Okay, so now that we have this, we can identify this is going to be a minimum. It's going to be a minimum of our function. And so because it's a minimum, now what we want to do to find the relative extrema we know that we're going to have a relative extrema at x equals 0. But again, that doesn't tell us how high or how low that function went. So we actually need to plug in 0 into our original function here. So we can tell me, or tell whoever's reading your paper, where we know what happened at x equals 0, but we need to also report what the minimum value was, because it happened at x equals 0, but the minimum value is actually the value that happens when we plug it into our function. So our minimum, when we plug in 0 into here, we get 0 minus 4 over 0 minus 1. So our minimum is actually +4, because we have a negative and negative. So our relative extrema is at +4, so we can report it like that. So we can report minimum at x equals 0, f of 0 is equal to +4. And that's it. So for the next video, I decided to separate them just because the section's a little long. We're going to be talking about concavity, which also has to do with the shape of our graph. And we're also going to learn what's called the second derivative test to find our relative extrema.